Okay, so let us start today's lecture. So last time we were discussing some voting methods, and through various examples, it became apparent that the voting method that we want, or the ideal or the most desirable voting method that we want, should have various properties. It should have certain properties which is considered to be very desirable for a voting method, which in summary is a method to select the winner once every voter has casted his or her vote. So the first of these desirable properties is anonymity. So all voters have to be treated equally. So in other words, if two voters exchange their marked ballots before submitting them, then the outcome of the election is the same. So for example, if you and I are voting in the same election, and I have marked my choice in the ballot paper, and you have marked your choice on your ballot paper, and before putting them inside the ballot box, if it is physical voting, for example, if we just exchange our ballot papers and cast them in, it should not make a difference regarding the outcome of the election, regarding who wins the election. Okay, so that's anonymity. In other words, rearranging the votes do not change the outcome of the election. So let's begin with what is not an example of an anonymous voting method. So dictatorships are not examples of anonymous voting method, and we will come to the details a bit later. But before that, let us, for a change, try to understand what is an example of an anonymous voting method. Well, simple majority is an anonymous voting method, right? Because you just count which candidate gets how many votes, and if there are two candidates, then the person who gets more votes wins. And clearly, it's the total number of votes which matters. So, if you and I exchange our votes, then it doesn't really matter, because if you and I exchange our ballots, then the outcome of the election is not changed, because the number of votes polled by each candidate remains the same, because you are counting the ballots. You are not counting who is casting the ballot. Right. So that way, so that's an example of anonymous. Dictatorships are not anonymous because if there is only one person whose vote matters, then of course, if the ballot of that person is exchanged with the ballot of other person, then the outcome of the election might change. Okay. Is it clear? Any questions? Simple majority and supermajority are anonymous voting methods. So this example we already saw or already discussed. Simple proposition is that a social choice function is anonymous if and only if its outcomes depend only on the tabulated profile. So a social choice function, let us remember what it was. So every voter casts a vote. So there is this array of votes, each vote corresponding to each voter, and then the social choice function takes in the sequence of votes for every voter, and then it combines or aggregates or assimilates this sequence of votes cast by the voters and throws up a winner. So what this proposition is telling you is that a social choice function is anonymous, that is, two voters, if they exchange their marked ballot, then the outcome of the election is not changed, if and only if the outcomes depends on the tabulated profile. So what is the tabulated profile? The tabulated profile is precisely that you add up the votes, you look at the sequence of votes cast by the different voters, and then for every candidate, you add up the total number of votes it has polled from all the voters. So from the sequence of votes cast by every voter, you have a summary information, which is you have the list of candidates and the total number of votes obtained by each candidate. Okay, so that's the tabulated profile. So of course, and the social choice function of course, in general it depends on the sequence of all the votes cast, but as a particular case it might depend only on the total number of votes obtained by the different candidates, right? So those are particular types of social choice functions. So for example, the simple majority function is method is an example of a social choice function which just depends on the tabulated profile, because it just looks at the total number of votes polled by the different candidates and compares them. Okay, so it's a social choice function which depends on just the tabulated profile, and that's a necessary and sufficient condition for a social choice function to be anonymous. So if you want a social choice function to be anonymous, that is, if any two voters exchange their ballots, then or exchange their votes, even then the outcome of the election would not change. If you want that property, basically you have to work with the tabulated profile. So your social choice function, if it satisfies this anonymous property in selecting the winner of the election, then this social choice function should only depend on the voting sequence exclusively via the total number of votes cast by the different candidates, the total number of votes obtained by the different candidates. So as an example, you can think of the simple majority method. So it just depends on the total number of votes obtained by each candidate, because it compares the total number of votes obtained by the candidates and picks out the one with the highest one. Okay. Any questions? Okay. So another desirable property of a voting method is neutrality. So neutrality means that all candidates should be treated equally. So if everyone switches their votes, the outcome of the election is reversed, or so this is like a small possibility. So if it was a tie, then the result should remain a tie. So again, what is neutrality? So again, we are working with social choice functions. So our input is the sequence of votes cast by the different voters, and our output is the winner of the election. And the property of the social choice function that we want in terms of neutrality is that all candidates should be treated equally, and the explanation is that, or the sort of detailed description of this property is that if everyone switches their vote, then the outcome of the election is reversed. Okay, and in the event that it was originally a tie, it should remain a tie. So if I switch, so if there are two candidates and everyone A and B, and everyone switches their A vote to B, or if they had voted B, they switch their vote to A, then of course, for example, if you are deciding by the simple majority method, if A had gotten more votes than B now, if you switch the votes of A and B, of course B will now get more votes than A, and B will be the winner by the simple majority method, right? So here is an example. So simple majority and supermajority methods are neutral, whereas an example of a method that is not neutral is monarchy, because monarchy doesn't really depend on the sequence of votes, because it always picks the same winner who is the monarch. Okay, so even if all the voters switch their votes, the winner will not change. Okay, so any questions? So here is another desirable property. This is monotonicity. So if some voters change their votes from the loser to the winner, while other voters stay with their original votes, the outcome of the election is the same as before. So by monotonicity, we mean the following. So think of again compare with the simple majority method. So or maybe, so if you think of a method in which there are multiple candidates and the candidate who gets the most votes wins. Okay, if you look at that sort of scenario, then of course, if there is some voting profile, so some profile of votes, some sequence of votes cast by the voters, and you are working with that, and you apply your social choice function to declare a winner, and then you take that voting profile and you switch some of the votes of the other candidates in favor of the winning candidate. So of course, the winning candidate is getting more votes, So he should remain winner, right? So the point is that if you increase the votes of the winning candidate, if you alter the voting profile and increase the votes of the candidate who was already winning, he should still remain the winning candidate. So that's, it sort of sounds natural, so that's a desirable property that you expect out of a good voting method. So of course, simple majority. So monotonicity ensures that more votes for candidate will not hurt their chances of winning, and the simple majority and supermajority methods are monotone. So as we just discussed, and so are dictatorship and monarchy methods, because of course if you sort of switch some votes in favor of the winning candidate, then the winning candidate doesn't change in these methods. And a method which fails this test is simple minority, because of course in simple minority you are picking the winner as the person who received the least number of votes, and if you switch some of the votes of the other candidates in favor of the candidate who won by simple majority, then he might no longer remain the person who received the lowest number of votes, right? Because he won by simple minority because he had received the lowest number of votes. Now what you are doing is that you are going in and switching some of the other votes in his favor, so his votes will increase, so he might not remain the candidate with the least number of votes, so he will no longer be the winner by the simple minority method. So simple minority fails monotonicity property. Any questions? So then another property is decisiveness. So a social choice function is decisive if it always chooses a unique winner, that is a method never results in a tie. Okay. So a social choice function is nearly decisive if the only situation in which a tie can occur is if both candidates receive the same number of votes. Okay. So the simple minority, a social choice function is decisive if it always declares a winner no matter what, and it is nearly decisive if it always declares a winner except for the situation when there are two candidates and they get the same number of votes. Okay. So the simple majority method is nearly decisive, clearly, because if there are two candidates, then by simple majority you declare the person who gets more votes as the winner, except for the fact that except for the situation when they get both the same number of votes, in which case you declare a tie. So simple majority is nearly decisive, but it may fail to be decisive. Of course, if they get the same number of votes, both the candidates, then you just declare a tie. There is no winner, right? So simple majority is nearly decisive, but it may fail to be decisive because under certain circumstances, it might result in a tie. The quota system is not decisive, whereas the dictatorship and monarchy methods, so there should be a D here, are all decisive. Okay? So this you can check by going through the definition of the systems. So the big question is as follows. A perfect or a best voting system should at least be anonymous, neutral, and monotone. And majority rule enjoys all these three properties, but it is only nearly decisive. Okay? So of course, all the properties that we decided, or that we discussed, seem to be very natural to expect of a voting method, that it should be anonymous, it should be neutral, it should be monotone. So so it should not depend on who is casting the vote, as long as so it should depend on the number of votes. Then it should be fair to all the candidates. So if you switch the votes of the different voters, the winning candidate should also switch accordingly. And then it should be monotone in the sense that getting more votes should not hurt. However, and we already discussed that the majority rule was an example in favor of all these three properties. The fourth property is decisiveness, and we saw that the majority rule was nearly decisive, but it might not be fully decisive in some cases. So the question, so majority rule sort of majority rule satisfies the first three properties. The fourth property, it satisfies nearly but not fully. So the question is, can you find a social choice function that is even better, and it satisfies not only the first three properties of being anonymous, neutral, and monotone, but it also satisfies the fourth property of decisiveness. So it's not merely nearly decisive, but fully decisive. Okay? So the answer to this is surprising. So, and just to take a step back, so why do we want decisiveness? Well, one argument in decisiveness is that if there is a tied election, then there is a lot of controversy, right? So, then who will become the ruler, for example, if it's a election for choosing the government. So if there is a tie, then there can be controversies and problems. So, it's better that the rules are such that there is always a winner. So, of course, the first three qualities of anonymity, neutrality, and monotonicity are really very important and indispensable, and simple majority has all of them. The fourth one is decisiveness. We also would like to have it. So the question is whether we can have it and design a voting method or a social choice function that is even better than the simple majority. And here comes a surprising theorem, and it was proved by mathematician Kenneth May, who you can see in this picture. So in the 1950s, Kenneth May, who was a mathematician, proved the following surprising fact, that the only voting method for two candidates, which is anonymous, neutral, monotone. So far we have just covered the first three properties, and we already have a method that satisfies all the first three properties, which is simple majority. And nearly decisive is the simple majority method. Okay? So only voting method that is anonymous, neutral, monotone, and nearly decisive is the simple majority method if there are two candidates. So what does that mean? Notice that decisive, if you look at the definition, a decisive method is also nearly decisive, right? Because so it just doesn't. So it always declares a winner. Nearly decisive method means that if the two candidates get the same number of votes, then there may or may not be some ambiguity. Decisive method means that there is no ambiguity under any circumstance. So of course, decisive means nearly decisive. Decisive method is in particular nearly decisive, and what May's theorem is telling you is that a voting method that is anonymous, neutral, monotone, and nearly decisive has to be the simple majority method. So the simple majority method for two candidates, the simple majority method is the only voting method that satisfies the properties of anonymous, neutral, monotone, and nearly decisive. So now, let us go back to the question of answering the question on the previous slide. So can we get a social choice function that is anonymous, neutral, monotone, and fully decisive? The answer is no, because if you are anonymous, neutral, monotone, and fully decisive, that means in particular that you are anonymous, neutral, monotone, and also nearly decisive, because you are being decisive, so of course it's also nearly decisive. And then you are stuck with the simple majority method by May's theorem. But but the simple majority, so if there is a social choice function which is anonymous, neutral, monotone, and fully decisive, it has to be the simple majority method, because if it is anonymous, neutral, monotone, and full and decisive, then in particular it is anonymous, neutral, monotone, and nearly decisive, which the simple majority method is the only example according to May's theorem. So if it is anonymous, neutral, monotone and decisive, then the only possible example is the simple majority method. But we know that the simple majority method is only nearly decisive and not fully decisive. So the only example which could satisfy the conditions of this question was the simple majority method, but we know that the simple majority method does not satisfy the fourth condition. So there is no voting method that satisfies the conditions of anonymous, neutral, monotone and decisive. Okay? So this is an important consequence of May's theorem. So let us recap May's theorem. So in an election with two candidates, a social choice function that is anonymous, neutral, monotone and nearly decisive, the only example of such a method is the simple majority method. Okay? Any questions? Any doubts? Okay. So in other words, if you have any method which satisfies anonymity, neutrality, monotonicity and is nearly decisive, then it must be the simple majority method in disguise. So maybe you are taking your voting sequence and doing a lot of mumbo jumbo and spitting out a winner, and you say that you have a very new method which is anonymous, neutral, monotone and nearly decisive, then May's theorem will step in. He will come in and tell you that, well, you might be doing a lot of complicated steps, but in the end, at the end of the day, you are just doing simple majority method in disguise. Okay? So, any questions? Okay. So thus the simple majority method is the only voting method having these properties, not just of the ones we have studied, but all theoretically possible voting methods. So in this module we have studied a few voting methods, probably the most popular ones, but in principle you could come up with other voting methods, and indeed in the literature people have looked at other more esoteric voting methods. Kenneth May's theorem actually covers all of them. So it says that whatever voting method, whatever social choice function you consider, as long as it is anonymous, neutral, monotone and nearly decisive, it must be the simple majority method. Okay? Okay. And here is an impossibility result. So an impossibility result that is a consequence of May's theorem is that our search for a decisive method, fully decisive method, satisfying anonymous, monotone and neutral is futile because the simple majority method is not decisive if the number of voters is even. That is, so this item, this aspect or this fact we already discussed in detail a while ago, but let us recapitulate it in the form of a neat corollary, that it is impossible for a social choice function with two candidates and even number of voters to satisfy anonymity, neutrality, monotonicity and decisiveness. Okay? Any questions? So if there are no questions, then let us take a break of 10 minutes at this point, and after the break we will continue with the lecture. Okay, so let us now look at some examples. So suppose there are three candidates B, G, and N standing for blue, green, and neutral in an election with 5922531 voters. The tabulated profiles of the voters are as follows. So some of you who have sort of a longer historical memory or some political general knowledge or curiosity would actually identify that these B, G, and N are not really colors. They are not really blue, green, and neutral, but they are actually code words for Bush, Gore, and Nader, who is Ralph Nader, from the famous 2000 US elections, so the US general presidential elections from the year 2000. Okay, but let's for the purpose of academic purposes, let us think of them as blue, green, and neutral. So the tabulated voting preferences are as follows. So so if there are three candidates, then each voter gives a preferential choice for a choice for their preferred order of the three candidates. So for example, some voter might think that B is better than N is better than G. So such a voter would vote for this possibility. If the voter believes that B is better than G is better than N in that order, then he will vote for this possibility. Similarly, if some voter thinks that G is the best, followed by N followed by B, then he or she will vote for this possibility, and so on. There are various possibilities, and various people have cast their votes according to their preferences. So they have, on their ballots, they have indicated their preferred order of the three candidates. So each order of the three candidates have received these many votes. And notice that if you sum the vote counts of the first and second columns, it is 2912790, and the sum of the third and fourth columns is 2912253. So it's really quite close. And the question is, who should be declared the winner? So in the first two columns, B is the winner. In the third and fourth column, G is the winner. And if you tally the votes where B is the winner, it's 2912790. And if you tally the votes where G is the winner, it's 2912253. So, and these figures are very close. So just a bit more than 500 votes in a huge presidential election. So naturally the question arises as to who should we declare the winner. So for example, there are some extra votes remaining, much more than the difference between the two candidates. So how should you take into account these votes? So here is another example with three candidates. Again, there are votes not directly for the candidates, but for the preferred order of the three candidates. Okay, so for three candidates, for multiple candidates, you have votes for preferred order of the candidates, and you have various votes tabulated for different preferred orders. And if you look at the candidate B, so you can look at the you can tally the votes in which B is the first place. You can tally the votes for which G is the first place, and you can tally the votes for which N is the first place. So the total votes for which B is the first place is going to be this. If the total votes for which G is the first place is going to be a sum of these, and the total votes for which N is going to be the first place is the last column. Now, if you look at it closely, if you compare these counts, then B gets most first place votes among the three candidates, but it's not a majority. So if you look at just the first place votes, so B will get a certain percentage of first place votes, G will get a certain percentage of first place votes, N will get a certain percentage of first place votes. So since there are more than two candidates, it's not as if one of the two candidates must get at least 50% of the first place votes, right? Because there are three candidates, so in principle it could be, one candidate could get, the first candidate could get 1/3 of the first place votes, second candidate could get 1/3 of the first place votes, and third candidate could also get 1/3 of the first place votes. So it can be really fractured that way, okay? So simple majority simple majority means if some candidate wins more than 50% of the first place votes. Whereas plurality means that the candidate wins the candidate gets more first place votes than any other candidate, but it's not more than 50% of the total first place votes, okay? So here is an example of that. So the candidate B receives the plurality of the first place votes. So the number of first place votes for candidate B, which is the sum of these two columns, is more than the first place votes for any other candidate, but it's not more than 50% of the total votes, okay? So, however, a majority of voters prefer, that is, give a higher rank to candidate G over candidate B. So how do you calculate the number of voters who give higher rank to candidate G over candidate B? Well, you just look at the combinations where G is placed above B. So like this one, or this one, or this one. So in the latter three combinations, G is placed above B. So you don't care where N is placed. You just are interested in finding out how G and B are placed relative to each other. And in all these last three columns, the G is placed higher than B, and therefore in all these voting in the preference lists of all these voters, the candidate G has been preferred to or ranked higher than candidate B, okay? So if you just look at how many voters prefer candidate G over candidate B, that is rank can give a higher rank to candidate G over candidate B, you will find that a majority of voters actually rank candidate G higher than candidate B. Although candidate B receives the plurality of first place votes, that is more voters place candidate B in the first place than any other candidate, okay? So in this is the exact kind of situations where the election is very tight and there is a conundrum if there are more than two candidates, okay? So here are the B, G, and N with pictures. So this example, as we already discussed, is a fictional example, but it's based on the outcome of 2000 US presidential elections in the state of Florida. And we have invented the preference orders and removed other minor candidates, but the first place totals are actually factual, okay? So it was a famous and very close election. And in very close elections, these kind of problems come up that, someone gets the plurality of the first place votes, but not a majority. And then it might turn out that the second placed candidate in terms of the losing candidate in terms of the first place votes can actually turn out to be preferred to the winning candidate by a majority of the voters, and this sort of complications can come up in this kind of close elections involving more than two candidates. So let us now actually drop the pretense of G, B, and N and call them by names. So Bush received plurality of votes, resulting in Florida and thus the country selecting Bush as the winner. So you might be knowing that US is a huge country and the votes are not counted directly, but instead it is counted directly in each of the states, and then each state has a certain weightage, so it has a certain number of electoral college votes, and these electoral college votes are then given to the candidate who is sort of granted to the candidate who wins that state, and then when you do this over all the states, then the candidate with the most number of electoral votes wins the electoral college votes wins the presidential election, right? Becomes a president. So what happened that year was that the election was very tight. So Florida turned out to be the decisive state. So Florida is a very big state on the eastern coast of the United States, and taking into account all the electoral college votes of the different states. So different states have different numbers of electoral college votes because some states are very small, some states are very big. So they have different number of electoral college votes. And after all the calculation was done, it turned out that whoever wins wins Florida will become the president. Basically, that's how it stood. And Bush received a plurality of the votes, and the way votes were counted in Florida, he was declared the winner in Florida, and thus the country, thus Bush became the winner of the presidential election and became the president of USA. However, it is reasonable to assume that Nader's supporters preferred Gore to Bush, meaning a majority prefer Gore to Bush. So, for example, here in this, in some sense, it's kind of a toy list of voting preferences, but as you can see, voters who put N as the first choice, Nader as the first choice, definitely put Bush as the last, and Gore as the second. So, definitely all the voters who prefer Nader prefer G to B. Okay. So, so if you take into account that, if you just look at the relative ordering between B and G, then of course G is preferred by most voters, that is the majority of voters, compared to B. So majority preferred Gore to Bush. Thus the plurality method cannot reflect this fact. So since the election was decided by plurality, so the person with the highest number of first placed votes was declared the winner. There was a lot of angst and lots of controversy surrounding that election. So in particular, one of the reasons was that the plurality method cannot reflect the fact that most supporters prefer that Gore actually won. A majority of voters actually preferred Gore to Bush in their relative ordering. So these examples highlight some of the difficulties that we encounter in elections with more than two candidates. So now we embark on the study of social choice and multiple candidates. We will now consider such elections with an arbitrary choice, finite choice of candidates A, B, C, etc. So definitely more than two. Every voter will submit a preference ballot on which he or she lists the candidates in descending order of preference. So for example, suppose there are three candidates A, B, and C, then a vote will be one of the 6 possible orderings. Remember that if there are 3 symbols A, B, and C, you can have 3 factorial or 6 orderings between them. So there are 6 possible preference lists which you can draw up between the 3 candidates A, B, and C, which are listed here. And a vote for an individual voter will be in favor of one of these 6 possible preferential orders among the 3 candidates. And we will also assume that voters are rational in the following sense. If a voter prefers A to B and B to C, then she also must prefer A to C. Okay, so this is a rational assumption on the voter, and it's called transitivity. The collection of all preference ballots cast by fixed, so this is a typo. So the collection of all preference ballots cast by a fixed electorate is called a profile. So this is a profile, for example. So there are 1, 2, 3, 4, 5, 6, 7 voters, and each of the 7 voters have cast preference, have indicated their preference of the relative preference, the ranking of the 3 candidates in their ballots. So, for example, for voter 3, this column, the red column, is the preference ballot. Any questions? The social choice function. So, social choice function or voting method is a function with domain, the set of all possible profiles, and a codomain, the non-empty subset. So, basically, what it takes as a social choice function or a voting method is a function which takes as input a profile, a preference profile of votes. So, you can think of this as a preference profile, and outputs a winner. So, input is a profile of votes and output is a winner, okay? Or it could be a type. In other words, a social choice function tells us the society's preferred choices. So, what is a plural? So, what are some examples of social choice functions? So, this is an extension of social choice functions that we saw for 2 candidates, okay? So, one method to one social choice function which is popular is called the plurality method. So, a plurality method is a social choice function that selects as winners the candidates who are ranked as first choice by the most number or plurality of the voters. So, notice that if, as soon as there are more than 2 candidates, 3 or more candidates, it might be the case that the person, the candidate who receives the most number of first choice votes doesn't receive a majority of the first majority of the total number of votes, okay? So, it may be that the 3 candidates, there are 3 candidates and the first choice votes are more or less equally divided among the 3 candidates. So, each of them could end up receiving almost 33% of the first choice votes by the different voters. So, that is the plurality method. So, it's what you get is the winner is the candidate who gets the plurality or the most number of first choice votes. That is, the plurality method chooses as the winner the candidate who are ranked as the first choice by the most number or the plurality of voters. So, we will soon see an example. But let us first look at a few remarks. So, the ranking of the other candidates can be disregarded. So, if you indicate A as the winner, for example, in the first profile here, then how you relatively rank B and C. So, of course, B and C have to be ranked below A, but the relative ranking of B and C which you put in your ballot doesn't affect the outcome, okay? The all important thing is who you put at the top of your ballot. So, this is the most common system used in the world, and it is the system used in Singapore. Okay? So, for example, consider the voting profile below. A is winning the election because A is the first choice candidate for 3 voters. So, A first choice of 3 voters. B is the first choice of 2 voters. Similarly, C is the first choice of 2 voters. Okay? Now, if C becomes B, if the red C here becomes a B, so if you switch that vote, so for example, if you switch the positions of A and of B and C in the last preference profile, then both A, so one vote will, so this will become 3, 3 and 1. So, C will lose 1 vote and B will gain 1 vote. In that case, both A and C have 3 votes and then A and B both win. Okay? So, notice that we did not require a majority of the first place votes for a candidate to win in this method, and we cannot do so because it could result in no winner being picked, violating the fact that social choice functions can only output non-empty sets, that is violating the fact that social choice functions can always need to output a winner. So, the social choice function cannot say that there is no winner. So, So, this is pertaining to the example that we discussed before, because there are more than 2 candidates. For example, if there are 3 candidates, the first choice votes can be split more or less 3-way equally, and none of the candidates might have a majority of the first choice votes. So, if you ask for a majority of the first choice votes for a candidate to be declared the winner, there could be none. So, majority is not a feasible option as a social choice function when there are more than 2 candidates, because because the social choice function always needs to be a winner. In any election, you want to design a voting method that there is at least one winner. Okay? So, we will return to the plurality method later. So, let us now go into tabulated profiles for more than 2 candidates. So, the plurality method, just like the simple majority method for 2 candidates, the plurality method depends only on the number of voters having a particular preference order and not who cast them. So, basically, so again the plurality method depended on who got the most first choice votes. So, all that you needed was to count for every candidate how many first choice votes he got. So, it does not matter who is casting the first choice votes, right. So, the plurality method therefore depends only on the number of voters having a particular preference order and not who cast them. So, again we can simplify the input to a tabulated profile, and instead of the detailed information about the sequence of which voter chose which preference profile, we will just tabulate for each particular preference profile how many votes were cast in favor of that preference profile. So, for a tabulated profile for 2 candidates, we just calculated for each candidate how many votes he got. For more than 2 candidates, we will, instead of individual candidates, we will work with preference profiles, and for every preference profile of candidates, we will calculate tabulate how many votes in total, how many voters in total cast their votes in favor of that particular preference profile. So, here is an example of that. So, notice that A, B, C has 3 voters in supporting the list ABC. So, ABC has 3 votes. BCA has 2. So, BCA has 2. Similarly, CAB has also 2. So, CAB has 2 votes. So, this is the tabulated profile corresponding to the preference lists in the previous voting example. So, as you can see, with more than 2 candidates, it is becoming more and more tricky how to determine the winner in a satisfactory way. So, there has been a lot of thought put into these methods, and one of the people who worked on these methods was a famous intellectual called Nicolas de Condorcet, who lived in the 18th century, and there is a voting method associated with him, and the winner of that voting method is winner determined by that voting method is called the Condorcet candidate, named after Condorcet, and the winner is determined in the following way. Given a profile, a candidate is called a Condorcet candidate or a Condorcet winner if he or she beats every other candidate in a head-to-head or simple majority matchup. So, what you do is as follows. You look at the profile like this, a voting profile, and you consider every pair of candidates. And for every pair of candidates, you can determine by the simple majority method who is the winner. Okay? And the Condorcet method is as follows. You take every, so the winner is, the candidate wins multi-candidate election by the Conversant method, and therefore is called a Conversant candidate or a Conversant winner, if that candidate beats every other candidate in a head-to-head matchup. So, for example, A will win the election, A will be the Conversant winner here. So, we will see who is the Conversant winner, but suppose, for example, when will A be declared the Conversant winner in this case? A will be the Conversant winner or the Conversant candidate for this voting profile if for every so if you just consider A and B, then A will be placed above B in a majority of the voting profiles. Similarly, A and C, if you compare A and C, then A should be placed above C in a majority by a majority of the voters. So, Conversant candidate is a candidate who satisfies the following property. If there are three candidates A, B, and C, then A is the Conversant candidate or the Conversant winner if both the following things happen. If you just take A and B and forget C, then most of the voters should put A above B, disregarding when he puts C. Similarly, if you consider just A and C, disregarding B, then most voters should put, by most in the sense of simple majority, most voters should put A above C in the relative ordering, ignoring where they place B. Okay? So this is called the Conversant candidate. So here is an example of a Conversant candidate. So consider the profile of these votes. So there are 5 candidates, large number of candidates, and these are the voting profiles. So there are 5 voters who have indicated that their relative preferential order for the candidates are these ones. So B is the Conversant candidate here. Why? So when will B be the Conversant candidate? Well, B will be the Conversant candidate or the Conversant winner if you pair B against any of the other candidates, disregard all the remaining 3 candidates, just look at B and this other candidate who you are pairing with B, and then calculate how many voters place B above this other candidate in their preferential order. So just the relative ranking of B and this other candidate would matter. The positions of the remaining 3 candidates would not be taken into account. So then B should win the simple majority of this head-to-head matchup with every other candidate. Okay? So let's now look at what is going on. So let's first consider the head-to-head matchup of A and B. B is placed above A in 3 of the profiles. So let's identify which ones. So here B is placed above A. Here B is placed above A. And here B is placed above A. So in these 3 profiles, B is placed above A. In the remaining profiles, A is placed above B. So if you just look at the relative ordering between A and B, then A is dominating B in 3 profiles, B is dominating A in 2 profiles. So in the relative matchup, A wins simple majority against B, okay, in the head-to-head matchup. Similarly, let us consider B and C. Then B is placed above C in 3 of the profiles. C is placed above B in 2 profiles. So again, in the head-to-head matchup between B and C, B wins simple majority. Similarly, you can consider the head-to-head matchups of B and D and E and B, and in both cases, B wins the simple majority. Okay? Clear? So therefore, in head-to-head matchup with any other candidate, B is always winning the simple majority. So B is the Conversant candidate or the Conversant winner. So so that sounds nice, but it can lead to problems. the problem, the main problem with the Condorcet method is that not every profile has a Condorcet winner or a Condorcet candidate. So let's look at this example. So this is one of the examples we kind of similar to what we were discussing before, that there are 3 preferential lists and the votes are kind of split equally 3-way. Okay. The method, so here you see that ABC, BCA and CAB, this is almost like a cyclic permutation. So A is placed above B, so A is beating B in head-to-head matchups, but if you compare A and C, then C is beating A. So A is not the Condorcet candidate. Similarly, if you look at B, then B is beating A in head-to-head matchups, but if you compare B, if you compare B and C, then B is beating C in head-to-head matchups, but if you compare A and B, then A is beating B. So A beats C, but fails to, A beats B, but fails to beat C, B beats C, but fails to beat A. So none of A and B are the Condorcet winners. Similarly, C is also not the Condorcet winner because it beats one of the other candidates in a head-to-head matchup, but fails to beat the third one. Okay. So this profile doesn't have a Condorcet winner. So Condorcet criterion seems to be very nice and solid, but it suffers from the problem that you might not have a winner. It's so stringent. So consequently, the method which is select the Condorcet candidate on a winner is not actually a social choice function because it doesn't always give you a winner in the election. So however, if there is a Condorcet candidate, then he or she is unique. So there is no problem of having multiple winners in the Condorcet method. And the easy way to see it is that suppose there were multiple winners. So suppose there were 2 winners by the Condorcet method. So suppose there were 2 Condorcet candidates. So now, let's say A and B, these are the 2 Condorcet candidates or Condorcet winners. Now you just consider the head-to-head matchup between A and B. Because A is a Condorcet winner, it must beat B by simple majority, right? On the other hand, since B is also a Condorcet winner, it must beat A by simple majority. So both of these is not possible. Okay? So if there is a Condorcet candidate, then there can be only one. So that's a good part, but the problem is that it's not a real social choice function because there are situations where it doesn't give you a winner at all. So social choice function that satisfies the Condorcet criterion, if whenever a profile has a Condorcet candidate, the method selects the Condorcet candidate as the unique winner. So the Condorcet criterion is actually sort of a watering down of the Condorcet method. So Condorcet method, as we saw, is not a social choice function. It's not an honest social choice function because it doesn't always give you a winner. So it doesn't always decide an election. So you cannot use that as a social choice function. However, what you can use it for is the following. The Condorcet method is useful for can be useful in the following way. So you can ask your social choice function, which is an honest social choice function, to satisfy the Condorcet criterion. That is, if there is a winner by the Condorcet method, if there is one such, it doesn't need to be, but if there is one such winner, then your method must coincide with that winner. So whenever there is a winner by the Condorcet method, so you can think of applying a very strong criterion and determining the winner by that very strong criterion, which is the Condorcet method. Then your method must agree with the winner determined by the Condorcet method. Okay? So then your social choice function is said to satisfy the Condorcet criterion. So here is some more thoughts on the example. So if there are 3 voters, A, B, and either 3 candidates, A, B, and C, and these are the rankings of the 3 candidates and the number of votes, then the number of first place votes received by each candidate is 33, so that it is the same. Moreover, 2/3 of the voters prefer A to B, 2/3 of the voters prefer B to C, and 2/3 of the voters prefer C to A. So there is no clear winner. Moreover, preference is not transitive, that is, more voters prefer A to B, so A is preferred to B, and more voters prefer B to C, but also more voters prefer C to A. So this kind of relative preferential order, that logic is turned on its head, and is a very legitimate simple voting profile, right? So this is the kind of problems that you can encounter in elections with multiple candidates. And plurality method fails the Condorcet criterion. So that you can see by this sort of example. So here is another tabulated profile. So there are 3 preferential orders of the candidates, 3 candidates A, B, C, BCA and CBA. These are the 3 preferential orders. So the list ABC, that order gets 3 votes, BCA gets 2 votes, and CBA gets 2 votes. So A is the unique, who is the plurality winner? Well, A is the unique plurality winner. But B is the Condorcet candidate, because if you compare B and A, then B is preferred to A in these 2 lists. So B is preferred to A, so A, B, if you just compare A, B and B, A. So B is preferred to A in these 2 lists, so 4 votes in total, whereas A is preferred to B in the first list only, which is 3 votes. So B is similarly, if you match up B and C, B is preferred to C in the middle column, middle preference list. B is preferred to C also in the first preference list. So B is preferred to C in the first and the second lists, which is 5 votes in total, and C is preferred to B only in the last list, which is 2 votes in total. So in head-to-head matchup with any of the other candidates, B is beating C. B is beating C and B is beating A. So B is clearly the Condorcet candidate, but by the plurality method, A is the winner. So the winner determined by the plurality method does not coincide with the Condorcet candidate. So therefore, the plurality method does not satisfy the Condorcet criterion. In other words, it fails the Condorcet criterion. In fact, if you just look at the head-to-head matchup of A and C, notice that A is preferred to C only in the first list, whereas in the second and the third lists, A is less preferred than C, so C is ranked higher than A. So therefore, if you just consider the head-to-head matchup between A and C, A loses 3-4 to C. So therefore, this makes the result of the plurality method even less appealing, because it is A is being beaten in head-to-head matchup with another candidate. Okay. So these are some problems with the plurality method, and we will continue in the next lecture. We will stop here today and continue in the next lecture, beginning with some more remarks on the plurality methods. Okay. Okay.